While a majority of GIS studies currently revolve around exploring phenomenon on Earth, we now have the means to perform similar analyses on other celestial landmarks. This particular project takes us some 250 million miles away to one of the few places that Ben Affleck couldn't follow Matt Damon in film, Mars, the red planet. Even though the surface of the planet is pretty barren, the presence of silica may hold secrets of a more aqueous past than many might believe. Here to share with us this evening is presenter Kathleen Markham, and we all know this presentation is going to be out of this world.
Yeah. Good evening, everyone, and thank you, John. I'm Kathleen Markham, and once again, thank you for being here this evening. I'd like to take the opportunity to speak with you about some of my research about a topic which is out of this world that can be studied using concepts and tools developed to study our own planet, and that is silica deposits on Mars. To begin describing my research, I'll first introduce the star of the show, the Curiosity rover, then provide some background information about how the story begins, Curiosity's mission into the Gale crater and where it is currently deployed, and then touch on the model that was developed and its practical application. The Curiosity rover, more formally known as the Mars Science Laboratory, or MSL, was launched in November of 2011 and landed within its study area in August of 2012. The rover is equipped with 14 onboard instruments, including 3 noted above: ChemCam, ChemMin, and APXS. ChemCam is able to visually identify geological features within the landscape and use a layer to clean away debris. ChemMin is able to analyze chemical compounds of collected samples. And APXS, also known as the Alpha Particle X-ray Spectrometer, looks at chemical element composition of collected samples. Last December, NASA released a press statement saying that Curiosity had found something unusual, and that is unexpectedly high concentrations of silica deposits. Unusual discoveries are not anything new for Curiosity. In 2015, it also made the news for finding unexplained bubbles of methane in the atmosphere. But what makes silica so interesting is that the presence indicates that water flow may have been in the region. According to NASA science team member Albert Yen, the 2 most likely ways that silica became a part of the landscape were either by water washing away surrounding minerals and leaving silica behind in quantities, or by silica being dissolved and deposited in high concentrations. Silica, also known as silicon dioxide, is the most abundant compound in the Earth's crust, and it is widely known for being associated with water flow and microbial life. Therefore, being able to pinpoint areas where silica should be present on Mars, hypothetically, can provide scientists with defined search areas where the likelihood of finding evidence of present or past life on Mars is increased. Curiosity's study area within the Gale crater is within an alluvial fan where past alkaline aqueous processes are suspected to have occurred. It's also worth noting that the center of the crater is home to Mount Sharp, also known as Aeolus Mons, a mountain which was formed by the initial impact which formed the crater. Currently, Curiosity is roaming along a band of geological formations at the foothill of Mount Sharp. The Gale crater itself is in the mid-latitudes of Mars and is approximately 90 kilometers in diameter. It's home to a wide variety of geological formations available for studying within the crater. And for the purposes of my work, all of the study area is going to be referred to as below Martian sea level, which is something that NASA mathematically approximates as being a relative 0 point for elevation. The area modeled for potential silica areas is located within the northwest corner of the crater. It takes an unusual shape because it's made up of 815 square kilometers of available high-resolution imagery, mosaic together, but more on that in a moment. This image shows a collection of the most data-rich drill sites visited by Curiosity. The middle row, which includes Buckskin, Big Sky, and Greenhorn, are all samples found within the same, are all locations of high silica samples. Big Sky and Greenhorn are samples found within the same large site location. So for the purposes of modeling these sites based on their site location, those will be considered a single site. The imagery used for analysis was obtained from HiRISE, the high-resolution imaging science experiment on board the Mars Reconnaissance Orbiter. HiRISE offers 1 meter resolution images of the study area. It can go as low as 10 centimeter resolution images. These images were used in combination with contour data collected by the Mars Orbital Laser Altimeter, which is on board the Mars Global Surveyor. This was used to create a digital terrain model of the space. Fortunately for me, these digital terrain models were pre-made by the Lunar and Planetary Laboratory here at the University of Arizona. To these digital terrain models, hydrology tools were applied to create a hypothesized view of water flow within the study area. And then the study sites, including the 2 known sites to have silica, were overlaid to investigate the relationship between these sites and the water flow within the space. Here we see the downloaded digital terrain models. There's 12 in total that were mosaicked together to create our study space. And Curiosity's sites were overlaid on that mosaic digital terrain model to show the rover's path and the distribution of sample sites within the space. It's worth noting that the digital terrain model does not help much in this one view. All of the sample sites were within a fairly small elevation range. And that is because a Curiosity rover cannot traverse over extreme changes in elevation. So there's only gradual change. Plotting these study areas posed a unique challenge. Unlike Earth, there is no global positioning system on Mars. There's no simple GPS instrument among the 14 instruments on board the rover. NASA uses geometry to calculate the rover's movements and position on Mars to a sub-nanometer level. And after digging through some extremely challenging documents, this is a snippet of some of those extremely challenging documents, and spending a lot of times with maps, such as the one at your right here, I was able to approximate and designate GPS coordinates for each one of the 60 sites available. What you see here is the position of the rover on individual Martian days, known as sols. So it was very complex trying to decide how to distinguish which individual sample sites were what. In beginning to analyze this data, the sample tool was applied in ArcMap to provide elevation data for each of the sample sites. And here we can see Curiosity's gradual climb up those foothills of Mount Sharp. And beginning at about Site 50, which you can see here, Site 50 is approximately where our silica sites are. That's where more erratic changes in elevations begin to occur. Curiosity is starting to reach more interesting geological formations in this area. There are inherent challenges with creating a hydrological model on Mars. Since there are no apparent physical processes on Mars that smooth out the cratered surface as there are on Earth, there is a high concentration of sinks, or cells in which water flow cannot flow out of. The following hydrology tools were applied to the mosaic DTM twice, with these sinks intact, as you see here, and then with the sinks filled. Only the filled mosaic was suitable for further analysis. A flow direction raster was first created to reveal how water would flow out of each one of those square meter pixels, followed by a flow accumulation. This raster was formed illustrating the theoretical accumulation of water flow within the space. And here we're beginning to get our first glimpse of potential water flow as they are connected to our sample sites. Working with these products, I was able to create a streamlined map of the study area. Keep in mind, this is 815 square kilometers. For reference, Tucson is 610 or so square kilometers. So this is a little bit larger than Tucson. The creation of streamlines was the first indication that there were artifacts in the data. Artifacts being the areas you see where there are perfectly perpendicular lines. The possibility of these artifacts was disclosed by the Lunar and Planetary Lab, and due to their situation within the space, I believe they did not interfere with further analysis. They are something that was difficult to avoid, but further investigation would have to be done to ensure that they did not affect the model. From the streamlines, the flow direction and flow raster, I created a stream order raster to further illustrate this hypothesized water flow within the space. This close-up view of some of the study sites shows the silica-rich sites in orange, and they lie in close proximity to first-order streams, or origin streams, whereas some of the non-silica sites in blue are not in any close proximity to these streams, generally not near the water flow. For completeness, the previously mentioned hydrology products were used together to create an individual watershed of the area. There were 18 total watersheds. However, I think it's exceedingly likely that that floating band of area up in the northeast significantly skewed that number since it was disconnected. All of the study sites, for the most part, fell within the same individual watershed, so I don't believe this is a suitable variable for discovering how silica got into that area. For the purpose of modeling silica sites most likely to have silica, a model was created based off the apparent position of silica sites within the space. Using the interpolated elevations for each site, negative 4,449 and negative 4,431 meters, a standard deviation was performed to give an estimated range where silica could be found. This range came out to 4,428 and 4,453 meters in elevation below Martian sea level. When the elevation range is mapped, it looks like this in the study area, which bears a striking resemblance to those bands you see in this image here along the foothills of Mount Sharp. So that is where I believe the geological formations have been revealed along the crater. A closer view of the study sites within the elevation band shows that many of our study areas fall within that same elevation range, and the ones that are silica positive are on the outer perimeter of this range. Returning again to the idea that silica sites were situated near origin streams, we can suspect that since these streams have low flow accumulation and silicon dioxide is a relatively heavy compound compared to some of the other minerals in the area, I suspect that Albert Yen's hypothesis that surrounding minerals were slowly washed away, leaving silica behind, is most likely. But in either rate, the distance of silica sites to streams was assessed for analysis. The two silica sites were situated 6.6 and 18.42 meters from an origin stream cell. These figures were also used to calculate a standard deviation, which yielded a range of 4.15 and 20.87 meters to an origin stream. That is a hypothesized range of distances that silica would be in. A series of buffers were then created to highlight the areas of space within this range to the first order streams within our elevation range. And upon investigating how the study sites fell within these areas, I discovered that 2 additional sites fell in these areas that were not recorded as having silica. And furthermore, a third site fell on top of the streamline. You can see these up, oops. You can see these up here in the corner here. Here you see the elevation range with the buffers overlaid. And then again, for completeness, the watershed within which silica sites fell was also used to try and further reduce the model. However, those 2 new sites were still within that watershed, so this did not significantly narrow down the possibility of areas where silica could be. In all, 4 of the 60 sites, the 2 known silica sites and 2 without silica, both fell in areas modeled to have the greatest likelihood of presence based on the apparent spatial variables. A variety of statistical analysis tools were applied to these results, all of which calculated that the variables of elevation and distance to origin streams were not significant to the presence of silica. Applying an ordinary least squares analysis to the results gave some hope that the possibility of a distance to an origin streams could be significant. However, the R-square value, as you see here, was extremely low, suggesting that should there be a spatial relationship between distance to streams, it is not one off of which a strong model could be based. I admittedly felt very defeated about these results, and so doing my due diligence, I tried to investigate what must have gone wrong in this process. After digging through NASA's mission logs for each SOL spent at these 2 sites, 42 and 43, I discovered a couple interesting things. At Site 42, the geology lab was used However, its purpose was housekeeping, which is programming updates and general cleaning of the instruments. So it was noted as a geology site, but it didn't do actually any geology work. At Site 43, the geology was indeed used, and samples recovered had contained crystallobite, which is actually a silicate, and a compound very closely related to silica with a different crystalline structure. Before further testing the model could be performed to see if this ensured that my model was perfection, all of the soil logs would have to be read in order to understand all of the research that was assessed and be able to throw out other false positives days when the geology lab was cleaned. While this model does not immediately serve as direction support for the Curiosity team members, providing further resources to investigate silica is a worthy endeavor. In researching this topic, I came across a study of a subterranean mine in South Africa, which postulated to be the closest thing to the Martian landscape on Earth. This mine is home to microbes which sustain themselves solely by consuming and excreting methane, the very gas Curiosity unexpectedly discovered. So while silica may not lead scientists to finding life on Mars, modeling its presence is still a valuable exercise in understanding a very faraway space. Thank you. Any questions? No questions.
On your streamline data, when you were showing this analysis,
Mm-hmm.
You had a, yeah, go back.
To just the streamlines, this one here?
Yeah, why do you have the 90-degree angle lines?
I tried to figure out exactly what it was because these aren't the seams of the mosaic together DTMs. LPL doesn't give a lot of information about what that could be. Solar flares might interfere with the sensor.
I mean, they look
But-
like error points because there's nothing straight,
Yeah,
unless they're human
yeah, so
or Martian.
correct the case. So it could be from high rise, it could be from MOLA. When you look at the data itself, there's nothing apparent, and neither source was able to give me any real reason why they should be there.
Okay. But you
So-
looked into it a little bit.
Oh yeah.
Okay.
Yeah. I tried to solve them, but I wasn't able to. Yeah, great.
So those kinds of lines, though, when you're talking about rasters, because they are east, west, north, south, or if you have arrows, they tend to be east, west, north, south, and I see both of those kinds of lines.
Yeah.
Mm-hmm.
So there's something about the
But it's not a true north-south, is it, Gary?
well, it's hard to say from here.
With the-
Especially when I can't figure out how to
It.
But it's a raster, and you get those kinds of artifacts, particularly when you're doing streamlines. And if you're just doing streamlines on Earth, you get the same kinds of things. You get north, south, east, west, and you get some that go on a 45-degree angle. That's really cool.
Yeah, I didn't see any of those ones. Since the raster itself was a DTM, and so in theory it had both the MOLA data, the MOLA contour data, and the high-rise data. It kind of had two equal parts putting it together, so it could very well have been the high-rise images, and LPL did disclose that there was a good possibility that those would be included, but I was unable to get rid of them myself.
Just import something from Wyoming and put it.
Scale. Yeah, some fjords or something, yeah. All right, thank you.